we have a talk on sensors and automobiles. Yesterday, Dr. Khatri discussed engine management system, in which he talked of a number of sensors that are used in the automobiles for controlling the power and the emissions. I will just discuss those sensors again, but not from the point of view of their application, but from the point of view of their principle. And while doing so, we will also discuss some fundamentals of that, like we also demonstrate that how do fundamentally sensors work. So in automotive control systems, the modern automobiles, they use a number of components for control. Number one is microcontrollers to implement control functions. Then sensors, which provide measurement of variables for feedback to the controller. And the actuators, which are electrically operated devices which regulate the inputs. For example, say in an automobile, a sensor may detect that what is the position of the accelerator, that how much accelerator has been pressed by the driver, and accordingly it will decide how much fuel to inject so that the vehicle speeds up to that point which is required by the driver. Then an sensor may measure the oxygen content in the air. For example, the exhaust gas oxygen sensor, it basically senses whether the mixture is rich or lean. So at higher altitude, because the air is rarer, so the oxygen content is low. So in that case, if the mixture becomes say too rich, the ECU will instruct the injectors to accordingly inject lesser amount of petrol or whatever fuel. So micro sensors with actuators and microcontrollers, they are fundamental to use of MPFI or CRDI engines. Like even if we discuss our body, so our body has so many sensors. For example, if we put our hand accidentally on a hot surface, what happens? The skin immediately conveys to our brain that the surface is hot, and the brain has a logic that in case our body is touching a hot surface, it will get burned. So the brain will instruct our muscles to go away from that hot surface. Accordingly, with a jerk, we will take our hand away. So the same thing is used in automobiles or any other control systems in the industry. Now in automobiles, we have, this is a block diagram that we are showing. So we have sensors which give their output to the electronic control unit. The electronic control unit will give the output to the actuator. The output will depend upon two things. First is the input from the sensor, and second, the logic that is there in the electronic control unit. The actuator, like a injector, petrol or any fuel injector, that will then give the fuel to the engine, and from the engine we basically get two things, the power and the emissions. So the whole idea is to get optimum power and to get minimum emissions. That is why the sensors came into picture. Otherwise, earlier, as we know, that carburetor and other mechanical methods were used to operate the engine. So this diagram we'll elaborate further. Sorry. So here in this figure, what we see is a block diagram in which there is a ECU or engine control unit. To the engine control unit, there are a number of inputs. For example, the first is a throttle position sensor. So it tells the ECU that what is the position of the throttle, which depends upon how much accelerator the driver has pressed. Then we have a manifold air flow rate sensor. So this will also give a information to the ECU. Then we have an exhaust gas oxygen sensor that gives a feedback to the ECU. Then we have a crankshaft oblique camshaft position sensors which tell the ECU what is the position of the piston. Then we have coolant temperature sensor. Apart from this, there are so many other sensors. For example, what is the RPM of the vehicle? And so on, so forth. And a map is not mentioned here, a manifold absolute pressure sensor. So a number of sensors give the input to the electronic control unit. And the electronic control unit then accordingly drives the fuel injectors, it drives the ignition system, it drives the exhaust gas recirculation valve if it is present. So the ECU gets the first-hand information from the sensors, and based on that information and the logic in its memory, it drives the various actuators. In automobiles, a large number of sensors are installed within the vehicle. So they act as perception elements. That is, they have the task of converting a physical or chemical variable, for example, pressure, temperature, distance, gas, into an electrical variable. So that is a fundamental thing, that all the sensors that we use in automobiles or any control system, they must give the output in the form of a electrical signal, usually in the form of a voltage, but maybe in the form of current also, but mostly it is the voltage signal. Otherwise, we also have a normal spring, which is again a sensor which can detect, okay, what is the weight. But here, the conversion is from weight to displacement. But in control systems, we want the output in the form of electrical signal. So that is one fundamental requirement in automobile sensors as well. Now, in automobiles, what are the desired characteristics of the sensors? First is high degree of reliability. Because if we are driving a vehicle on a highway at a high speed and suddenly some sensor fails or some actuator fails, so it can lead to disaster. Then favorable manufacturing costs. So yesterday Dr. Khatri gave a very good example that an ECU costs around 30,000 rupees. So if it is to be fitted in a car, the car cost can absorb that cost. But if it is to be fitted in a motorcycle, which is costing say 70,000 rupees, 30,000 is a large amount, more than 40% of the basic cost. So a favorable manufacturing cost is very much required. Then high degree of accuracy. So here you see, yesterday he was telling that, okay, there's so many milligrams in so many milliseconds or microseconds of petrol has to be injected. So how much accuracy is required in these sensors? And even the frequency at which they work, that is also astonishing. Normally when you cruise a vehicle, the engine is running at a RPM of say 2,500 RPM. So that means it is roughly 40 hertz. The frequency of the piston is 40 hertz. In 1 second it is going 40 times. So in 1 second, say if it is making 40 strokes, so even if there are, say if it's a 4-stroke engine and there are 2 strokes are equal to 1 cycle, so that means in 1 second, 20 out of 20 times a cycle is happening in a second. And within that, for a very small duration, the fuel has to be injected. So the frequency of the sensor, it goes up to milliseconds, and they are required to be highly accurate. Another example is say we have anti-lock braking systems in automobiles. So what the anti-lock braking is essentially that the system does not let any one wheel come to a stop. So all the four wheels must come to a stop simultaneously. Because if any one wheel or if any two wheels they stop rotating, the vehicle will skid. Now as the vehicle is moving on a road, the friction conditions or the traction between the four wheels and the road is different for all the four wheels. So when you apply brake, by default the same effort goes to all the four wheels, the same braking effort. Now let us say under one wheel there is some oil or something, so the traction between that particular wheel and the road is less. So that wheel will come to a stop early as compared to others, resulting in the skidding of the vehicle. So our ECU is constantly monitoring the RPM of all the wheels. So if it finds that one particular wheel is decelerating at a higher rate as compared to other wheels, it will immediately reduce the braking effort on that wheel. So we may have pressed the brake pedal, but that is only a signal that goes to the ECU. The rest of the thing is done by the ECU. We do not have any manual control over our braking. So that is why the first point, high degree of reliability. So to reduce the effort or to maintain the same deceleration of all the four wheels, the injectors that inject the oil into the braking cylinders, they work at the frequency of say 1000 hertz. In 1 second they will open and close 1000 times. So you can see how much high accuracy is required. Then these sensors must remain fully functional even under extreme operating conditions. So a vehicle may be operating in a desert, in a very hot weather, in a very humid weather, in a very cold weather, the sensors must remain fully functional. So this was say one problem which was faced in the 1962 India-China war by Indian Army, that their trucks, they stopped operating at high altitudes because they were not suitable for running in the extreme cold conditions. So the army people, they had to burn fire under the petrol tanks or the diesel tanks so that the vehicle can work. And then compact design. So design also has to be compact because they will be, you have to fit it in a system which is already existing, and it cannot be very large so as to obstruct with the functioning of the system. So if we take a look at this picture, you can see what a variety of sensors are used. So you have a GPS at the front, radar sensors, anti-theft sensors, wheel speed sensors. So I'm just going anti-clockwise now from here. So we have the global positioning system sensors, radar sensors, anti-theft sensors, wheel speed sensors, tire pressure monitors. So high-end cars also have tire pressure sensors, and some cars even have the ability that the tires will inflate in case the air is leaking at a high speed. And then we have the standard speedometer, tachometer, odometer, then parking sensors, fuel level sensors, passenger occupancy. How many passengers are sitting? Right. So like for example, normally when we sit in a car on a driver's seat, if we do not fasten our seat belt, a warning sign comes on the dashboard. But in many cars there are load cells or some kind of strain gauge sensors mounted under the seats, so that they monitor that whether on the say passenger seat, if a person is sitting, whether he or she if the somebody is sitting and the seat belt is not fastened, then again the car will give a signal that the passenger has not fastened a seat belt. So seat belt tension sensor is there. Rain sensors are there. So in case the rain falls, the wipers are started automatically. Then indoor outdoor temperature sensors, oil level, water coolant temperature sensors, oxygen sensor, accelerometer, and so many others which have not been shown here. So now with modern automobiles, where there are self-driving cars, so you can just take a car and leave the car, it will find a parking space and park itself. So they are now existing and commercially available. So they all rely on the sensory input and then the sophisticated logic. Okay. So if we talk of the classification of sensors, vehicle sensors are mainly classified into three categories: powertrain sensors, chassis sensors, and body sensors. Powertrain sensor means starting from engine to the whole powertrain, the gear system up to the wheels. So it contains engine sensors, transmission, and onboard diagnostics. So powertrain sensors are used for vehicle energy use, drivability, performance. Then chassis sensors are for vehicle handling and safety. So they are basically for sensing how much steering has been moved. Then suspension. So again, the high-end cars have suspension sensors where the suspensions have a magnetological fluid in them. That is, depending upon the condition of the road, depending upon the type, or you can say the frequency of jerks or the amplitude of the jerks coming to the car from the road, the viscosity of the oil changes. So in real time, so in microseconds, the viscosity is changed. Then vehicle braking, like we said, anti-lock braking system. And then there are further next level of anti-lock braking system is electronic brake distribution, where once you apply the brake, there's a proactive control. The ECU will see that how much load, how the load is distributed on all the four wheels, and accordingly it will send the braking effort to the different wheels. And the stability, the car is just going to roll or not, like that. Now in body sensors, occupant safety, security, comfort, convenience, and information, right? So comfort, convenience, we have automatic air conditioners, climate control sensors are there. And then there are also acoustic sensors. So if you are driving a car at say 80 kilometers per hour and you have set the radio volume to a certain level, and now if you decrease the speed, you may find the volume to be higher. So now there are sensors in the cars which will automatically reduce the audio level of the system. So whatever level you set, you will always listen to the radio or the stereo or whatever at the same decibel level. Information. So much information is now available. You have GPS, this and that, and occupant safety. Right. So this is again a very, very important sensors, like you have small accelerometers, so which will cause the what you call that airbags to inflate in case the vehicle meets with an accident. So accelerometers, they basically sense the rate of deceleration. Like normally if we apply a brake, the car will decelerate at some rate. Whereas in case of accident, when the car hits something, the rate of deceleration will be too much. And the sensors will sense it, and before the actual say impact occurs, the airbags will inflate, thereby protecting the occupants from hitting the steering or other parts of the car. So highly accurate, very fast response, and still they have to be cheap, they have to be reliable. So you can imagine that how difficult it is to design and manufacture these kind of sensors. Now there are also sensors like here also we have a GPS, but back in 2009 in North America there were GPS available. So in case the vehicle meets with an accident, they will relay the information to the nearest hospital, and they will give a very precise or very detailed state of the occupants. That, for example, that how many times the car roll after the accident, and what is the state of the passenger, whether he is conscious or not, like that. So there is no end to the convenience or the safety features that is there or that is coming. So first of all, let us see the powertrain sensors. These are the typical powertrain sensors. Okay. So as Dr. Khatri said yesterday, that crankshaft angular position sensor is a very important sensor because it decides that it tells the ECU that when to ignite the ignition coils or when to trigger the injectors, like that. So the crankshaft or the cam angular position sensors, they can be of many types, but in automobiles they are primarily inductive type or Hall effect type. Then we have throttle plate angular position sensors. They are basically potentiometric type. The mass airflow rate sensors, they are hot wire anemometer type. Exhaust gas oxygen concentration sensor, it is basically zirconium dioxide. Then coolant temperatures are mostly thermistors. Then intake air temperature, again thermistor type. MAP sensor or manifold absolute pressure sensor, diaphragm type, which is a piezoresistive type. Similarly, differential exhaust gas pressure, again diaphragm type. Then transmission gear selector position, what's the position of the gear. There are switches like inductive or Hall effect, and then the vehicle speed, the RPM, again they are tachometer type. So now our focus will be to go through the fundamentals, and we'll also have a small demonstration to see how it works. Now a crank position sensor is obviously used to measure the position of piston or rotational speed of the crankshaft. This information is used by engine management system to control ignition system timing and other engine parameters. So what you see here is a toothed wheel mounted on the crankshaft. So that's how actually it is. Here a number of teeth are shown to be missing, but they are not actually, because this photo has been taken from a kit that we have in our lab. So here the teeth were deliberately missed. So what you see is this is the sensor, right? And this is the contact point from where the output is taken. Now as this toothed wheel rotates, each tooth will pass in front of the sensor at regular intervals depending upon the speed of the crankshaft. So as we said that we have Hall effect type or inductive type or Hall effect type of sensors. So with each tooth passing in front of the sensor will give a one pulse. So what you see here is a train of pulses coming from this very sensor, and when you see the gap here or here or here, this is because of these missing teeth. So for each tooth we get one pulse. Okay. So from the train of the pulses, the ECU can decipher the positions of the this piston or from the crankshaft, the angular position of the crankshaft. Now, there are camshaft position sensors also. They also work in identical manner, but in some cases, both are not present because camshaft will rotate at half the RPM of crankshaft. So sometimes the information is taken from the camshaft, information is taken from the crankshaft, or vice versa. But crankshaft position sensor is normally preferred. Now, let us see what is this inductive and Hall effect. So, what an inductive type proximity sensor is, so which rely on the magnetic effects. So, what you see here is a inductive proximity sensor with different components shown using block diagram. So, in this sensor, there is an oscillator whose job is to create some frequency, that is some AC signal. So an oscillator is kind of a inverse of a rectifier which converts an AC to DC. So this converts a DC to AC. So what the oscillator does is it generates a alternating current and there is a coil. Now since this current is alternating, a magnetic field is set up, and that magnetic field is continuously changing because of it's an AC type. Now, whenever a metallic object will come near the sensor, like in this case, whenever a tooth will come near the sensor, what will happen? This magnetic field will induce eddy currents in the target. So these eddy currents will set up their own magnetic field and they will try to kill this magnetic field or oppose this magnetic field, as a result of which the oscillator frequency is affected. So when the oscillator frequency is affected, that is sensed by this Schmidt trigger. It's basically again a small part which will give you some value when the oscillating frequency goes down certain value. So that output is then amplified by an amplifier and given to the ECU. The second type, which is mostly used, is Hall effect sensor. Why Hall effect sensor is preferred? Because there is one problem with inductive type. As you can see, in inductive type, in a coil, a voltage is produced when EMF changes. So that means here, if this is stationary, the EMF change may not take place. So as long as it is moving, that EMF change will be happening. So if it is stationary, then it is difficult to get the information from the inductive type or magnetic reluctance type sensors. So Hall effect sensors are used. So in a Hall effect, what is the principle? That if there is a plate and we connect a, say, DC supply to this plate in the fashion as it is shown here, the current will flow, the conventional current, and we know the electrons will flow in the opposite direction because we take the conventional current as opposite to electron flow. Now, with this, if we try to measure the voltage in a transverse fashion, so obviously there will be no voltage because the potential drop is occurring across these two faces and not across these two faces. So if we try to measure a transverse voltage, we will get a 0 volt output. But if a magnetic field is brought near this plate, the electrostatic field of the plate and the magnetic field, they will interact, as a result of which the electrons which are flowing, they will be pushed to one side of the plate. So in the transverse side, one side will become negative, the other will become positive, and we will get a voltage which is called the Hall voltage. So from a Hall effect, either we can get a voltage by bringing a magnet nearby, or we can have a magnet nearby and have some voltage, and then we try to say strengthen the field or increase the effect, the flux density. So when the magnetic flux is amplified, then again there will be a change in the voltage. So Hall effect sensors, which are again the inductive sensors and Hall effect sensors, they are available as single piece with all the electronics on it. So they are used for proximity sensors, uh, or you can say crankshaft position or camshaft position sensors. Now here we will take a little bit break from the PPT and go to the our little demonstration. Right. So all the sensors typically they have. So we show you a inductive proximity sensor. So what you see here is a inductive proximity sensor. You can focus on this. Okay, we can focus on. Okay, anyway. So maybe we are not able to focus on the camera, but any proximity sensor, it has information on it about the, because my hand may not be stationary, so even if you focus it, it will, right? So I will otherwise tell you that on this particular sensor, it is written that what is the type of sensor, for example, whether it is a PNP type or an NPN type, and what is the range, that is from this end up to what range it can detect an object, then how much voltage it has to be supplied with, and how much maximum current we can supply to it. So any sensor fundamentally will usually have three contacts: one contact for reference voltage, one contact for ground, and one contact for the output. So if we look at the wire of this, you will see it has three wires. If our camera can catch the color, right? So it's a brown, a blue, and a black. So these are more or less standard colors. On the sensor, it is mentioned that we have to give the reference voltage at brown. This is for the ground, and the output is taken at the black. So whether it is a automotive microcontroller or any other programmable logic controller or any controller, when we connect a sensor to it, what we do is we connect this wire to the port, the black wire where we are getting output, to the port of the controller, and this to the ground. And to the brown wire, we will give our reference voltage. So we will just demonstrate to you the working. So one participant in the studio can come here. Okay. So to give a reference voltage to this, we will attach a snap to it, right? To which we will attach a to which we will attach a 9-volt battery. So the red of the snap we will attach to the brown wire, because that is where we have to give our positive supply. And the black of the snap to the blue wire, because here blue is the ground in case of this sensor. Right. So let me just cross verify. Yeah, it's fine. So to this sensor, हम इसको नीचे रख लेंगे यहीं पर, आप यहाँ थोड़ा सा नीचे कर लो चाहेंगे. So to this sensor, we will give a reference voltage of 9 volt. Because it is mentioned on the sensor, we can give it a voltage of 5 to 35 volt DC. So you will attach a standard 9-volt battery to this. इसको attach करें. And then to verify that when it will detect something, we will get a voltage output we will use a multimeter. So let me set up the thing. Give me a few minutes. Okay. So it is basically an inductive sensor. So it will detect metallic objects. So if I bring any metallic objects like my bracelet, okay, so you will see it will. I don't know if it's visible on the camera, but it's an indicator gives the output. Now my hand is away, and now it is there, right? So it is sensing. That is fine. So this light is just a visual indicator for the operator to see that it is detecting an object. Right? But actually, its use is that this signal has to go to the controller. So in case of a automotive ECU or any other controller, the output we will get on this black wire, and we will see with the help of the multimeter we will verify that the output across this black wire and this ground is 0 when there is nothing in front of the sensor, and when an object comes near the sensor there will be an output on here. So for this we will use a multimeter. So because I am giving it a voltage of maximum 9 volt, so I will set the multimeter knob to 20 volt DC. This is very slippery actually. Right. So we have set the knob to 20 volt DC because we are using a 9 volt battery. And then let us attach the multimeter probes to that. So we attach the common probe and the positive. Right. Now what we'll do is, because the output is on this black wire, so अब आपको इधर से आ गए ना, देखो, what you do is, इसकी मैं से हुक बना देता हूँ, इसको हुक में लिफ्ट कर लेना, ठीक है ना, और जो ब्लैक वाला है उसको इसकी भी हुक बना देता हूँ, ठीक है, इसको रेड अगर हवा में उठा लेना ताकि वो टाइट रहेगा, हवा में, इसमें नहीं, और इसको इसमें, चाहे हवा में उठा लो, हवा में उठा लोगे ना, okay. So now you can see at this time the reading on the voltage is, the multimeter is 0. You can just bring the camera near. Right. And also there is no indication on this sensor. No need, sorry. Okay. Okay. Now you can bring the camera slightly down. Maybe leaning down it. Right. Okay. The multimeter and this both. Yeah, that's fine, perfectly fine. Right. So you can see there is no visual indication on the sensor, and there is no reading on the multimeter. It was okay. Yeah. Right. So you can zoom further if it's possible. That's fine. I think it's quite sensitive. थोड़ा सा zoom out कर लो. बस. That's it. ठीक है. Okay, right. So you can see as the indication, weird indication comes here, you will find a reading on the multimeter. Right. So this reading that you are seeing on the multimeter, when it goes to the controller knows that the object is near. So that is the principle of any type of proximity sensor. The working principle may be inductive, maybe capacitive, maybe Hall effect, maybe anything else. So that is how a proximity sensor work. Now, next are the throttle position sensors. So the photo that you see on the screen, so this again is throttle position sensor, and on the right hand side you see an output. Okay. So as you can see now, the position of the throttle will not be binary, but it will vary. For example, here the situation is binary. Either this tooth is here or the tooth is not there. So there are two states. Whereas in case of a throttle position, the driver may have pressed the accelerator from absolutely zero to something absolutely maximum. So the throttle position will vary, and accordingly we need a sensor which is analog in nature, which will give a voltage signal in proportion to the input. So throttle position sensors, if we go to our first slide, they are potentiometer type. So when we say potentiometer, it is a very, very simple yet very, very useful electrical circuit in which we have simply a resistance, a voltage source is attached to the resistance so that a current flows. So this resistance you can see has two terminals. Let us say this is 1 and this is 3. So the current is flowing in this. Now if we have another terminal here which is movable, it's kind of a wiper, then the voltage measured across this terminal, which we'll call as 2 and 3, will depend upon the position of this contact. If this position is, let us say, here, then we are measuring the voltage across the whole resistance, and that voltage will be same as the applied voltage, because the voltage we will measure, output voltage, will be equal to the current through the resistance multiplied by the resistance. If we keep this wiper here, the whole resistance is in picture, and so I into R will be same as this applied voltage. But if we move the wiper down, as we move it in the downward direction, you can say the amount of resistance in this side will go on decreasing. But the current is constant because the current is flowing because of this voltage. So I multiplied by that much resistance will be the output voltage. So the output voltage will be 0 when this wiper is here, and it will be maximum when this wiper is here. So that means that displacement of the wiper, which is a mechanical parameter, it is being converted into a voltage signal with the help of this potentiometer. Now what you see in this screenshot is say linear potentiometers or linear pots. So all the three are same. So what you see here is the wiper. This wiper can be moved from left to right, like the volume control of a radio. and on this is the back side. On here we have different contacts, say 1, 2, 3, like that. So typically this is called 1, this is called 3, and this is called 2. That is how they are numbered on the back of the linear potentiometers, or for that matter rotary potentiometers, because a throttle position sensor will be measuring an angular displacement. So for that rotary potentiometers are used. The principle is same. Why we showed you this was because number one, potentiometers are of two types, linear and rotary, and number two, we will just demonstrate a linear potentiometer here. Now as you can see, it's a rotary pot or rotary potentiometer. So again here this A is the terminal 1 where we will attach our reference voltage. B is the black ground, which is the, and so we are giving a voltage across this whole resistance. Now this is a wiper which can move from here to here. Like in this position, if the wiper is here and we measure the voltage across this output, that is terminal 2, and across the ground, then the voltage will be equal to the current through this resistance multiplied by this much of resistance. So if the wiper is here, the output voltage will be same as the reference voltage, but as the wiper goes on moving towards the right, the output voltage will go on decreasing. So on this, it's a picture of a rotary potentiometer. So you can see here it says plus 5 volt ground and the output. So before we proceed further, let us see. Now let us see a rotary potentiometer. Yeah, one thing more. Before we switch to the potentiometer, there is one more concept in sensors, which is also there in automotive also, but it's a very important concept. That is of normally open and normally closed sensor. So this sensor we just saw, it had 3 wires at the output, brown for the reference voltage, blue for the ground, and black for the output. Now I have an identical inductive sensor which has 4 wires at the output rather than 3. So let the camera focus on these 4 wires. Now you can see also it has a brown, a blue, then a black and a white. Now brown is same for giving the reference voltage, blue is the ground. In white and black we have 2 types. For example, you just saw that when the object was not near the sensor, the output voltage was 0. And when the object was near, the output voltage was there. So that is a normally NO switch or normally open. But in a normally closed, you will get a voltage when the object is not near, and you will get a 0 volt when the object is near. It is opposite to normally open. So we will just demonstrate that. So we will just connect the this को इसके साथ और black को blue के साथ. We will connect this to. So while he makes the connections, I will go to the board and just give you the concept of a normally open and normally closed. So this is a normally open switch. This is the output and this is the input. So if we give some input to it, say a mechanical force, then the switch will close. This is a normally closed switch. When no input is there, the circuit is complete and the output will work. But if we give some input here, say a mechanical force, then the contacts will open and the circuit will be off. So our similarly sensors also we have NO and NC, and this particular sensor we will show it has terminals both for NO and NC. Also, while I am at board, oh, sorry. So one more thing we will see here is so we have just seen that typically a sensor will have three wires, like the one we saw here. There was a black on which the output was given, a brown on which the reference voltage was given, and the blue which was the ground. So any controller, whether it is a microcontroller of your automobile or a programmable logic controller on a industry shop floor, so it has number of input ports and number of output ports, and we will attach the output of the sensor to one of the input ports of the controller. The ground will go to the ground of the controller, and ground, it depends if the controller has a power source, say there is some power source, then we can get the reference voltage to the sensor directly from the controller itself. So whatever be the type of controller, this is the one arrangement that is used. So if we have to attach this particular sensor we just saw, that is how we will attach it to a controller. Now we will demonstrate the NO and NC. Okay. Okay. Okay, so let me just check it. I don't know whether it's inductive type or capacitive type. It is responding to my hand, but anyway, we'll show you it's working. Okay, so here also you can now attach the same thing. What you can do is this, this black to this blue. और दूसरा व्हाइट में डाल दो, रेड व्हाइट में डाल दो, उसको हवा में चलेगा, ये तो यहीं पर रहेगा. Okay, so what you see here is now you can see there is a voltage output on the multimeter, whereas it is not detecting anything. We will need both this and this in the frame. Okay, right. So there is a voltage output here, but there is no detection here. So now you see when when the sensor is detecting an object, now the voltage has gone to 0. So that is the white wire of this is a normally closed. Okay. That is when nothing is there, it is giving you an output. Right? And when object is near, then it is giving you a 0 output. That is a normally closed. So as you remember, in the first sensor we had brown, blue and black wire. In this we have brown, blue, black and white. So now we are measuring the output at the white wire, that is a normally closed. Now we will measure the output at the black wire, that is normally open. उसकी हुक बना लो, उसकी हुक बना लो. So now if you focus on the so now we have a 0 voltage. Our multimeter's battery is also not proper, so it is almost 0. But if we bring an object nearby, then the voltage will rise. Right? So when the indication is there, the voltage is something, and when the indication is not there, the voltage goes down. So this is a normally open. So we can have both normally closed and normally open type. Now we will have the potentiometer type. So you saw the linear potentiometers in the screenshot. So here also we will show a linear potentiometer. So this is a linear potentiometer, and there is a slider. So there is a slider. So this slider, there is a slider which can move. So this mechanical displacement can be converted into a voltage signal. And in case of a rotary, it will be like a screw. There the angular displacement is converted into a voltage signal. So if you look at the back of this, you will find there are different terminals, and maybe you can read these numbers. They are numbered as 1, 2, 3. In fact, on this particular one, there are 4 terminals. The first one is 1, that is where the positive of the reference voltage will be connected. 3 for the ground, and there are 2 terminals number 2. Depending upon which 2 we take, we will have if we have a 0 on this side, then we will have a maximum voltage on this side. But if we take the other 2, then we will have a 0 on this side and maximum on the other side. So you can see again we have a snap which we have connected. So to the terminal 1, we will give the positive of the reference voltage, and to terminal 3, we will give the negative of the reference voltage. Now the output will be taken at 2. So this white wire is connected to terminal number 2. So we'll just make a hook so that we can attach it to the multimeter. So red to the white and black to this. आपको भी लगाओ कि पहले के लगा लो इसको भी इसको कर लो. So let us keep this one. I will need this. I have one third, so later here. Now what you see here is the voltage is 0. I need this also in the frame. Yeah, that's it. With the wiper on this side. थोड़ा सा और focus करें, थोड़ा सा. बस ठीक है, ठीक है. So this, if I move this wiper, right? There is some loose connection. Okay, so there is a loose connection. I will hold a battery also with a loose connection. So now you see with this, with the wiper on this side, the voltage here is 8 point something. But if I move the wiper to the other side, as we move the wiper, our multimeter is giving a slow response. Otherwise, this. The snap is actually so our wire has basically gone loose, nothing else. So we'll just take 1 minute. ये बहुत बड़ी हुई है, इसको भी करना पड़ेगा. कई बार इनको बंद किया है खोलना. चलो ठीक है. Black red to the white. Okay, so we have again made the connections and hopefully this should work. ये छोटी है वायर इसकी. The snap is also to be changed. No, it is fine. Okay. So now as so now as you can see, the voltage is 0, but as I move the wiper, with the wiper, the voltage value increases, and the value of the voltage depends upon the position of the wiper. So if the wiper is at different position, the voltage output is different. So this is the analog conversion where the output of the sensor changes with the input signal. So thank you. So the throttle position sensor is basically a potentiometric sensor which works on this principle. And next we have a manifold airflow sensor. So its principle is based on hot wire anemometer, which are used for measuring the flow rate of gases or liquids. Here what we have is, we have a film on a substrate which is heated by a current through it. Now when the airflow occurs across this film, the film will lose its heat. Now this film is made a part of a Wheatstone bridge in which the R1, R2 and R3 resistances are fixed, and the film resistance is taken in such a manner so that when no airflow is occurring, then for a given current through this, the bridge is balanced. That is, there is no the voltage drop across A and B is zero, or you can say the voltage is same at A as that at B. Now when the flow occurs, the heat is taken away by the air from that film, due to which its resistance varies. Because we know that we have the formula R is equal to R naught into 1 plus alpha into delta T. So where delta T is the temperature variation, alpha is the coefficient of resistance change with temperature, and R naught is the resistance at a reference temperature. So by noting down the voltage drop across A and B, then the calibration is there that what is the flow rate. And the output of the Wheatstone bridge is given to an amplifier. So although in this picture amplifier has come, but amplifier will be there in all the sensors that we have discussed or that we will discuss, because it is our next level of, after primary sensing, the amplification has to be done. Okay. And here what you see is a actual MAF sensor. So in all the sensors you will see that there are terminals at which the output is taken. So this is for the crank position or cam position sensor. Similarly here we have the contact for the throttle position sensor, and here we have the contacts for the mass airflow rate sensor. So what we see here is an amplifier, a commercially available amplifier, the simplest and most popular amplifier. So the basic thing of an amplifier is it amplifies voltage by the order of 10,000, 1 lakh, like that. So if there is a voltage, say in millivolt, you can take it to 5 volt, 10 volt. Okay. Then we have a very important sensor, exhaust gas oxygen sensor. So as we were discussing yesterday, why it is mounted on the exhaust side. So Dr. Khatri said because it works at a certain temperature. It doesn't work below 200 or 250 degrees centigrade like that. So what this exhaust gas sensor, how it works is that it is exposed to two gases. One is the exhaust gas coming from the engine. Second is the air from the atmosphere. So here what we see is a EGO sensor mounted in the exhaust gas pipe. And on the right hand side what we see is that what is inside this sensor. In this sensor we have basically two platinum electrodes in which there is sandwiched zirconium dioxide, or it is titanium dioxide, but zirconium dioxide is more popular. Now what happens, the exhaust gases are given to this electrode through a protective coating, whereas the air is directly impinged on the other electrode. Now since air has oxygen and oxygen is in the form of ions also, similarly exhaust gas also have oxygen ions. So zirconium dioxide has a tendency to attract the oxygen ions. Now there will be more oxygen ions in the ambient air than in the exhaust gases. So the oxygen ions, when this absorbs, they get deposited at the interface of the platinum electrodes and the zirconium dioxide. On this side also they get deposited, which are coming from the exhaust gas. Because ambient air will have more oxygen ions, so this side will become negative as compared to this much, and we will get an output voltage. Now what is output voltage? That will depend upon whether the mixture coming from this had more oxygen or lesser oxygen, thereby indicating that what is the oxygen in the exhaust gases, and so therefore from there they calibrate that okay, how was the mixture in the this to the cylinder, right? It is also called a lambda sensor because this lambda is a ratio used in automotive, which is the ratio of actual air to fuel ratio and the stoichiometric air to fuel ratio. So because lambda is, this is a term used for the ratio of air to fuel ratio and the stoichiometric air to fuel ratio. So in case the mixture is lean, that is fuel is less, air is more, then the upper side will be, the numerator will be higher. So in case lambda is 1, obviously that means the actual air fuel mixture is equal to the stoichiometric air fuel ratio. So for a lean mixture, lambda will be greater than 1, and for a rich, lambda will be less than 1. Because this is used, that is why it is called a lambda sensor also. And as we said that there are signal conditioning circuits, so the output voltage, it gives output as a saturation, in the sense that in case it finds that lambda is more than 1, it will give an output voltage of say 1 volt. If the lambda is less than 1, it will give an output voltage of 0.1 volt, like that. So it doesn't give a proportion value, it just tells whether the mixture is rich or lean. Then we have a coolant temperature sensor, right? So the same sensor is used, or a similar is used for intake air temperature also. So these sensors in automotives are based on thermistor type, because temperature sensors can be of many type, but in automotive they are thermistor type. So here also you can see this is the sensing element, and then on this side we have the connectors for the voltage output. So like in a resistance temperature detectors, that is where you have say platinum. So there the resistance vary with temperature as R is equal to R naught into 1 plus alpha T. But for semiconductors, that is a thermistor, basically they are ceramics actually. So there it varies by another relation, that is R is equal to R naught into e raised to the power beta into delta T, where beta is a coefficient which can be negative or which can be positive. So if the beta is negative, they are called NTC sensors, negative temperature coefficient sensors. So this plot is for a NTC type sensor, where with the temperature the resistance decreases. The advantage that these ceramic types have over metallic type is that for R is equal to R naught into 1 plus alpha T, there will be a linear relation between resistance and temperature, and there for a given temperature variation, the resistance variation is not that much, it is lesser. Whereas for ceramic types or for thermistor types, the variation for a given temperature is high. For example, if the temperature is this, the resistance is this. If the temperature is this, the resistance becomes this. So the drop in the resistance is quite high for a given rise in temperature. Like we saw in the case of a MAF sensor that's used in a Wheatstone bridge, here it is used in a voltage divider or a potentiometric circuit type. So what you see here is that there is a fixed resistance R and there is a thermistor resistance RT. This V is the reference voltage, and the output voltage that we get from here, it is measured across the thermistor resistance. So this Vt will be equal to RT divided by R plus RT into V. So as the thermistor resistance changes, due to the temperature, this output voltage Vt will also change. Next, we have the MAP sensor or manifold air pressure sensor. So you can see here it is mounted here. So what this has is, again, they are mostly used as a piezoresistive type sensors are used for MAP. So the air from the manifold, it is exposed to this number 4, which is the actual sensor. Here, because of the piezoresistivity, again there is a Wheatstone bridge, the output voltage will change with the pressure, due to which the output voltage will change. So here also you can see there are 3 connections. 1 is the output voltage, 2 is the reference voltage, 3 is the ground. So almost in all sensors you will find 3 output connections. There may be some other cases also. In general, mostly it is like this. So what you see here is the piezoresistive principle of a MAP sensor. So here what you have is, you have a diaphragm. Now they are very small diaphragms. Like for example, a typical MAP sensor has a diaphragm of side 1.5 or 1.6 mm. It's a square having at the most say 3 millimeter square area. So it is a diaphragm. This diaphragm will deflect when the pressure is exposed to it. Now this diaphragm is mounted on a small plate, and there are sensing resistors there, like 1, 2, 3, 4. It's a Wheatstone bridge, but these resistors are very small. You can see yourself, if this side is 1.5 millimeter, then how much small this will be. So they are silicon metal foils doped. So basically NPN type. And now they are piezoresistive. For example, when we talk of a strain gauge, we know that resistance is rho L upon A, where rho is the resistivity of the material, L is the length, and A is the cross-sectional area. So the resistance depends upon the type of material and the dimensions of the material. When we are talking of strain gauge type things, there we are changing L and A. Can you focus it slightly more? Right, okay. So we know resistance is rho into L upon A. So when we are talking of strain gauge type pressure sensors, there with the pressure, the force is applied to the sensing elements and their dimensions change. But in case of piezoresistor, we are not changing the dimensions, we are changing the resistivity. So that is the difference between piezoresistor and other normal pressure sensors. Right. So MAP sensors or other differential pressure sensors in automobiles, because the sensors have to be very small, so we cannot rely on changes in the dimensions. We rely on change in the piezoresistivity. Right. Okay. So if we go to our this slide, you saw that the different type of sensors which are used in powertrain, their types: inductive, Hall effect, potentiometer, hot wire anemometer, zirconium dioxide, thermistor, piezoresistive. So we have discussed their fundamentals. Now, if we look at the other sensors like the chassis and the body sensors, so in chassis we have like wheel speed and engine speed sensors for anti-lock braking system, traction control system, and electronic damping, like I said. So there the sensor use magnetic reluctance or Hall effect sensors. Steering wheel angle, again potentiometer or optical encoder types. Optical encoder we have not discussed. Throttle position sensors, again potentiometer type. Similarly, okay, still chassis. Again the chassis and wheel acceleration, again the piezoelectric accelerometers. So in piezoresistive, we have a resistance change by the application of force or pressure. In piezoelectric, we have an output voltage with the application of force or pressure. Then brake system pressure, again strain gauges. Steering shaft torque, again optical devices like some kind of encoders. In body sensors, vehicle deceleration, which is used to trigger airbags, again piezoelectric accelerometers. Then wheel speed and engine speed, that is magnetic reluctance or Hall effect type. So basically, the fundamental types that we have discussed in powertrain, the same type of principles are used in other type of sensors. Some other sensors which are like say radar or ultrasonic, or you can say they are used for in autonomous vehicles or self-driving vehicles. So they will be discussed in on Thursday. So with that we come to the end of our automotive sensors part.